Hey everyone, and welcome. Today, we're diving into one of the most powerful yet beautifully simple tools in the entire world of data. We're going to talk about how you can look at a messy cloud of information and pull out a clean, simple pattern that can actually predict the future.
So let me ask you this. Can a simple, straight line, the kind we all learned about in middle school math, actually predict the future? It sounds a little too good to be true, right? Well, believe it or not, the answer is a resounding yes, and we're about to break down exactly how that works.
So, here's our game plan. We'll start with a basic question of why we're even doing this. Then, we'll see how to literally draw a line through our data points. After that, we'll figure out how to find the perfect line, apply it to a real-world example with ads and sales, and finally, ask the big question, how good is our model anyway?
All right, let's start at the very beginning. At its heart, what are we really trying to do here? We're trying to build a bridge from what we already know to what we desperately want to know. It's all about making a smart, educated guess about the future. Okay, let's make this real. Picture this, you're in charge of marketing. You've got a whole spreadsheet full of data showing how much you spent on TV ads each month and how many sales you got as a result. Then your boss comes in and asks, hey, if we pump an extra 200 grand into TV next quarter, what's that going to do for our sales? That question right there is the prediction question. So, how do we even begin to answer that question? Well, the first step isn't some crazy complex math. It's just about looking at our data and trying to see the story it's telling us. We're going to turn a picture into a powerful tool. And the formal name for this whole process is linear regression. Now, don't let the fancy name scare you. All it really means is we're taking two things, like our sales and our ad budget, and we're going to summarize their relationship with one simple straight line. That's it. If you took all that data and plotted it on a graph, you'd probably get something that looks like a big cloud of dots. The whole goal of linear regression is to just draw one single line straight through the middle of that cloud that best captures the general trend. Is it going up? Is it going down? How steep is it? The line tells us that story. And this is where we turn that visual idea into a powerful little formula. Every straight line in the universe can be described by this equation. Y is just what we want to predict, in our case, sales. And X is the thing we already know, our TV ad budget. The other two symbols, beta 0 and beta 1, are the two magic numbers our model has to figure out. One tells us where the line starts on the graph, and the other tells us how steep it is.
Okay, and that brings us to the most important question of all. You could draw millions of different lines through that cloud of dots. So how on earth do we find the one single line that is objectively the best possible fit?
But first, a little dose of reality from the legendary statistician George Box. He said, all models are wrong, but some are useful. What he meant is that our line is never going to be perfect. It won't hit every single data point exactly. The goal isn't perfection. The goal is to find a line that's useful enough to make good predictions. And the way we find that most useful line is with a really clever technique called the least squares method. Just imagine you draw a random line. For every actual data point you have, there's going to be a little gap between it and your line. We call that gap an error. What this method does is it measures all of those little errors, squares them, and adds them all up. Then it starts wiggling the line around, changing its angle, moving it up and down, until that total sum of all the squared errors is as tiny as it can possibly be. The best line is the one with the smallest possible total error. All right, enough theory. Let's get our hands dirty and see how this actually works with our advertising and sales data. This is where it all clicks into place.
So here's a little peek at what the data might look like. On the left, how much we spent on TV ads. On the right, how many units we sold. We take a whole bunch of this historical data and we feed it right into our model. And after the computer does all that least squares number crunching, boom, it spits out this beautiful, simple equation. This is it. This is our predictive model. This is the single best line that describes the relationship in our data.
So let's break it down. What does that first number, 7.03, actually mean? Well, that's our intercept. In plain English, our model is telling us that if we spent $0, absolutely nothing, on TV ads, we'd still expect to sell around 7,030 units. That's our baseline, maybe from people who already know our brand.
And now for the other number, the slope. This is the real engine of our model. This tells us the relationship. It's saying that for every single additional dollar we spend on TV ads, we can expect to sell an extra 0.0475 units. So spend another $1,000 and you can expect about 47.5 more sales. This is the number that answers our boss's question.
So, we have our magic equation. We can make predictions. But how good are they? Should we really bet the company's marketing budget on this? That's the final and maybe most important step. We have to grade our model's performance.
And to do that, we use a metric called R-squared. Again, sounds complicated, but the idea is super simple. Think of it as a score from 0 to 1 that tells us how much of the story of our sales numbers is being explained by our ad budget. A 1 would be a perfect explanation. A 0 would mean it explains absolutely nothing.
For our model, the R-squared value comes out to 0.61. So what does that mean? It means that 61% of the reasons sales go up and down in our data can be explained by how much we spent on TV ads. The other 39%? Well, that's explained by other stuff. Things our model doesn't know about, like what our competitors are doing, if we're running a sale, or just plain old random luck.
So, to wrap it all up, linear regression is just about finding the best straight line to summarize our data. It gives us a simple equation to predict something we care about, like sales, using something we already know, like our ad budget. And finally, that R-squared score gives us a report card on how well our model is actually doing its job.
So, we've successfully found a pattern in the noise of our past data. That's an incredibly powerful thing. But it leaves us with one last, big question to chew on. Our model is only as good as the data we fed it. What happens when the world changes? When our customers start behaving differently? How do we make sure our simple straight line doesn't end up leading us completely astray? That is the constant challenge in data science. Thanks so much for joining me.